Hi, folks. I hope you've had a good 3-day weekend. Welcome back. We're on day 5 of the material, and this looks a little different from our usual setup. I don't have slides here ready. I have a website up here. This website is called CircuitVerse.org, and it's what we're going to be using today to talk through our material. You can create a free account on CircuitVerse if you want to. There's no charge for an account. And we're going to talk about how we can use these digital gates to simulate the process of applying Boolean logic here. This is a little small to read, so I'm going to open this up into Simulator. Let it open up here. Oh, it didn't open up in the simulator. It gave me a blank one. Let me back up. Here we go. I'll just put this in full screen for right now. The way this works is that you have a set of inputs that you can deploy. Each of these inputs can be toggled from 1 to 0, or from false to true if you want to think of it that way. And then there are a set of gates that modify the inputs and then lead me to an output. So this type of gate here is just a negator. It negates your input. So let me first of all show you the wires. They light up when there is signal flowing through them. So when I turn this on, this wire lights up green. And then when I turn it off, it goes back to its, sort of dark green color. So this one over here is the negator. So if I turn this on, then the signal that comes out of it is off. But if this is off, then the signal that comes out of it is on. This is an OR gate. And so if either one of these is on, the signal that comes out of it is on. If this one is on, the signal's on. But if this signal's on, this one's on. This down here is an AND gate. And so there is no signal coming out of this because I only have one input that's on. I have to turn the other input on to get the output to be 1, for example. That's short version of what's going on in this sort of example circuit. Now let me go ahead and pull up the empty simulator. And this is what you'll be seeing when you get started. You'll have a canvas over here that initially starts out at a very tiny zoom size. I'll show you what I mean in a moment. Under your input, this is your standard binary input that when you click on it, you toggle. I'm going to just click on one and then drag it over here. And you can see how small it is. I'm going to blow this up just a little bit so that we can see what it is. Okay. Now, you can change some of the properties of this. In particular, you can give it a label. You can call it something. So we could call this, for example, input 1, for example. And we can also change its direction and its orientation. And these are a little bit hard to read depending on your monitor, but I could change it so that the input is pointing to the right. I can point it straight down, for example. So I can give it a label. I can give it an orientation. If we look at the gates, this is my AND gate, my OR gate, and my NOT gate. And if you forget, is every time you mouse over one of them, the tooltip shows up down here that lets you know what's going on. So when I mouse over this, that gives me an AND gate. And just like before, it's asking me if I want to save my project. I don't want to save it yet, so I'm going to cancel. I can give it some properties. I can give it a label. I can change the direction. I'm going to have this one pointing up. No, I want it pointing down. This is an AND, but I can change it from a 2-element AND to a 3-element AND or a 4-element AND by increasing the number of inputs. It behaves the same way no matter how many inputs we have. The output will be true only if all of the inputs are true. And then I can draw a connector from here to the from the input to the gate. I like to sort of stop my connections first and then connect them on the way so I can see all the legs, because otherwise it tends to just create an L shape that overlaps on the leg. But that's just a personal thing. I can also, if I need to do something more complicated with my input, I'm going to put down here another AND gate, make it face down. I can then take this input and split it off. And then when I turn this on, it goes as an input to both gates. So I can split my input if I need to feed multiple gates. Let me give a second input now. So here's my second input number 2. And I'll make it face down. And I will connect it from here first to about here, and then from here the rest of the way down. And now I can have both of the inputs to this gate being on, which means I should be able to get some output. So let me put an output here. There are a couple of different outputs you can choose. This is the output that just shows your output as a number. This shows it as just a light that's on or off. I'll show you the difference between the two of them in a moment. But this is the one we're going to want to use. All right. And I'm going to have this one pointing up. And I'm going to connect this. Whoops. To here, and then from here to there. All right. As soon as we have a valid connection, it changes from just an X to a 0 to let me know that it's connected. When I turn this on, it's still a 0 because this is an AND gate. When I turn this on, also now it shows up as a 1. So it's implementing a digital circuit version of the Boolean connectors that we've been using so far. Okay? And so spend some time playing around with this input, and I didn't mean to create a third one here. I'm going to go ahead and delete that. The and, or, and not gates. There are some more complicated gates later on, but for the purpose of our project, we're restricting ourselves to these 3 gates on the top row. And then our digital output gate. Okay? Our goal for this project is to create what's called an adder. An adder takes 3 inputs and then produces 2 outputs from them. And the function of the outputs is to count how many of the inputs are on. And it will display that count in binary. So 0 is 0, 0, 1 is 0, 1, 2 is 1, 0, and 3 is 1, 1. And so if all three of the inputs are on, we want both of the outputs to be on so that the output reads 1, 1. If any two of the inputs are on, it doesn't matter, that is, if 1 and 2 are on, or 1 and 3 are on, or 2 and 3 are on, and the other one is off, then the output should read 1, 0. If exactly one of the inputs is on, the output should read 0, 1, and if all of the outputs are off, the output should read 0, 0. And so you'll have two outputs in this project. I'll go ahead and make this one face up also, though that's not going to make much difference. This one is usually called S for the sum. It is the sum of the digits, but it's mod 2. And we'll talk later on in course about what we mean by mod, but this S will be 1 if the number of inputs that are on is odd, and it will be 0 if the number of inputs that are on is even. And then the other input here, let's pick this one back out, is usually called C for the carry flag. Oh, these are running into each other, so I'll move this one over a little bit. There you go. So that if I'm adding multiple registers together, this tells me whether there's a digit that has to carry to the next register or not. Okay? So that's, this is not correct. I'm just sort of showing what's going on here. But our goal is to have a project with 3 inputs, two outputs, and the outputs show in binary how many of the inputs are on. And so that as we toggle, that the outputs keep up with that. That's what a full adder does. Okay. If you read through the project specs, I've got some hints here. If you are really stumped at how you might go about doing this, start by creating a truth table. Your 3 inputs will be the first 3 columns of the truth table, and then you'll have a column for C and you'll have a column for S. And you'll list the rows in which C should be on and you'll list the rows which S should be on. And then write out those rows using disjunctive normal form, which is something we covered on Wednesday of last week. Once you write this out in disjunctive normal form, you get an expression for C and S that's made up entirely of and, or, and not gates. And you can use those gates in this project here to actually represent the disjunctive normal form. You'll get a very large and cumbersome circuit that way. You might be able to simplify the disjunctive normal form before you start working in CircuitVerse on it. But you can just go straight from the disjunctive normal form. And so let me clear a lot of this stuff out. I'm going to trash that. I'm going to trash this. Trash some of these connectors here. All right. Sorry, that took longer than I needed to for just trashing a bunch of connectors here. here's what I mean for using the disjunctive normal form. Let's take the example of the row when this input is on and this input is on. This will be the third input. All right. Let's just look at that particular example. When these two rows are on, I want the carry to be 1 and I want the sum to be 0. And so the carry would represent that this is on and this is off and this is on. Okay, so I would need a three-way AND. So I'll find an AND gate. Change the input size to 3. Make it point down. And I want to test that this is on. That input 3 is on. And I want to test that input 2 is off. And so what I'm going to do is test for the negation of input 2. Make this point down. Whoops, what happened there? Oh, it's crossed over that wire here. So I'm going to bring this down. In fact, I'm going to bring this whole thing down for a little bit. There we go. And now I can connect this back up. That's better. And then we can connect that. And that should give me the correct value for the carry. Now, in the case of the sum, I want this to be 0 because there are 2 inputs, so I need for this to be 1 and I need for this to be 0. So I will test the same conditions, but I want this to be a 0. And so I'm going to put a negator I have tested for this one being on, this one being off, and this one being on. And when all 3 of these conditions are true, the carry it turns out to be a 1. But I don't want the sum to be a 1. I want the sum to be the opposite. And so I negate the value from the AND gate and make that into a 0. Okay? And so when all 3 of these things are true, it prints out a 0 for that. Now that's only implementing one row of the truth table. And it won't work for other rows. If I change this from a 1 to a 0, well, that actually works. I have 1 input. But if I have all 3 of them on, it still says I only have 1 input. So it's not a finished project. It's only showing 1 row correctly. It shows this row exactly correctly. But if you can do this for a single row of the truth table, you can do this for all of the rows. But my recommendation would be to try to simplify the disjunctive normal form before you start working on this, and not try to do the whole thing. All right? You have a week to work on this. It's due Tuesday night. Save your work in CircuitVerse. Like I said, you'll have to create an account to do that, but there's no charge to do this. And then when you're finished, submit a screenshot of your project, or you can actually just take your project and save it offline. There are a couple of things you can do with the project. Okay. Good luck. If you have questions, get in touch with me over Zoom, or post a question to Piazza, or get in touch with me by email. Let me know if you got any questions. Y'all take care. I'll see you Friday. See you Monday. Not Friday. Monday. Bye.